Hi, all fellow aviation enthusiasts out there. So 2023 flight test season is just about to begin. This is the old Levitator up there, and today I brought some parts from the new Levitator, and I just want to take some time here to document and speak a little bit about the design changes and the motives behind those design changes. For this video to be at all meaningful for anyone, we just need to level the field of understanding here, what I'm trying to accomplish. So the ultimate dream, the vision, the goal is to build a man-carrying version of the Levitator. So the mission is to fly two persons in comfort, drinking coffee in front of a fireplace at treetop level for at least 30 minutes. And if I'm flying it alone, I want to be able to fly for at least 45 minutes, hopefully an hour. So that's the mission. So this season's model scale Levitator is all about exploring mechanical solutions and technology that will enable me to build a full-scale version which I can fly in comfort and also with a comfortable mindset. So it has to have redundancy or fail-safe, which make it possible to actually do this. I can build it, but would I dare to fly it? I want to dare to fly it because I want it to be as so safe that I feel just totally comfortable with the structure that I will build with my own hands. So already the three-bladed version of the Levitator, spoiler alert, this is had a surprisingly fail-resilient geometry and structure. You can lose a control surface or lose a motor or lose the landing gear. You can lose a lot of stuff, and it's still possible to land it safely. So it turned out to be pretty resistant in its original configuration, and now I'm just trying to up that game as much as possible to give me a further margin of error for my bad thinking or bad things happening when you're actually flying the machine. And also, going from this model scale, which is 5 meters diameter approximately, to the two-person man-carrying version, which will be around 25 meters diameter, that means that you cannot only take solutions right off the scale model and just scale it up. For instance, the landing gear are constructed by 2-meter-long carbon fiber rods, solid rods, and I cannot just scale that up to, what would that be? That would be like 10-meter long carbon fiber rods, like acting as a landing gear, like a landing skid. That just won't work. So I will need to develop a new technique for starting the machine, and I want to try that in the small scale as well. But let's take a look at various features that may provide a added layer of safety or redundancy or fail-safe. Let's start with the flight controller. So as you can see here, it's the Pixhawk cube, the orange cube. So this will give me the altitude hole that I was missing with the good old KK2 controller. And of course, it's not just a flight controller. This is actually a autopilot, so it's a completely different piece of technology altogether. And the test now for the first tryouts is of course just generally to tune this controller to accept the machine, and it is set up as a traditional helicopter with a H1 frame. I will get back to that, but that seems to be a good starting point, and with a setup like a direct drive electric motor tail. So that corresponds to this yaw motor over here, and we can take a look at that later on as well. And as you can see, I have a second slot here. So once I got this tuned, if I manage to do that, the next step will be to add another flight controller identical to this one. The full-scale version would have 4 of these, but trying out 2 in parallel will provide the necessary information I need, that is, if they are at all possible to drive in parallel. And this has of course the GPS functionality, and all that, so with the GPS and compass up here, but of course I can't run 2 GPSs in parallel without being electrically or digitally hooked up together, so only one will be active, but they have to be electrically and digitally disconnected from each other to provide the fail-safe feature. So yeah, it will be things that I have to experiment with a lot, and each flight controller will only control half of the control surface on each wing, and ultimately 1/4 if I go with 4 controllers. So that's probably one of the biggest new things with the machine, the new flight controller. It doesn't really look much from the outside, but when it comes to doing all the thinking and setting up, it's a big difference from just using the KK 2.1 flight controller. So this is the other end of that reasoning. So there are 4 servos that could potentially be controlled with one flight controller each. But for now, all 4 servos are connected to one flight controller, and later on I will cut this control surface in half, so that one flight controller will control the 2 inner servos and the other flight controller the 2 outer servos, and I can check how they match up. And each servo is a slim wing servo. They can pull 4 kilos each, so a 16 kilo combined force there. So that's a significant difference when it comes to the mechanical setup compared to the original version, which only had one servo that's sitting on top there pulling in a long push rod. It worked really good, and especially since it turned out that you could actually fly it with only 2 or 3 control surfaces active. But again, I want a greater fail-safe, so I don't want to have one wing's control surface fail at all. So I'm hoping for being able to cut this up in 4 pieces eventually in the full-scale version. Okay, another big difference is the wiring. You can see there is a lot of wiring, and the original Levitator only had 2 wires going from the underside. This is the underside, and 2 from the top side. And of course, in a full scale, you cut one of those, the wings will be very floppy and probably get destroyed in the wind. So this version has 8 wires going to the top and 8 to the bottom. So you can lose any wire and still have the wing under proper tension and proper attitude. So that's also a safety feature, but it's it's a pain to do this because it's just so many wires to keep track of, and the length has to be just right, of course, to get the angle of attack I desire. One good thing is that these kind of wires do come with small ferrules of proper size, so I can actually use the correct technique for terminating these wires. So yeah, so you can really get the most out of it. It's a 0.5 millimeters wire. Okay, and at the root of the blade there is not a, it's like a aluminum square tubing there, and it's a screw that goes straight through there that keeps the tubes in place. The original version had this kind of setup, and this works in model scale, but in full scale you cannot just, they will be like 12 meter long. You cannot just find the proper angle and jack them in. It has to be more like a hinge. So this will does work like a hinge. So this part goes into the main section in that little rectangular hole slot there, and from in here the angle can tilt down and lay on the ground, and then when you hoist this wire holder up here, you can tension the wings and they like go from leveling from the ground and go up. So it's a way of raising the wings from the ground rather than having to like carrying them in a perfect alignment and push them into tubes up there. So that's also like a reality check when you're going up in scale. And also the motors are not fixed. They are pivoting around the shaft there with a linear servo. And the point here is to later on try out a new starting method So this servo can tilt this way. Again, the wing is laying upside down. So the point is that this motor will hopefully be able to self-right the craft from the ground when it's laying down without the landing skid, and from that position it will start to swing back to this propulsion position and start to gain speed. So that's something I want to try out. I don't know if it will work, but I have placed all the stuff there needed for that, but the wires to that linear servo is not hooked up yet to any channel of the radio. And here we have the two representatives of what is in between the flight controller on one hand and the servos on the rotating part on the wings on the other hand. So the flight controllers are mounted to this, and the outputs from the flight controller are connected to these brushes that conveys the signal to the part of the rotor down here. So this wouldn't rotate, but the under part would rotate. And you can see the tracks here follows the whole pattern here. So right now the single flight controller sends signal to both these copper. They're supposed to be copper. This is just a wooden template, but these copper strips here. Later on, I want one flight controller controlling the outer one, and the second flight controller sending signals to the inner one, so that I can have the redundancy I spoke of earlier. So there are like 4 segments for the cyclic pitch. So the flight controller communicates with this, and the servos are hooked up to this. You would think that this would be like pitch, these two, and then you had roll on these two. But since it's a rotating entity, you have the gyroscopic precession. So you're actually doing pitch over here, which will be shown later on in the front. And in the front you have like pitch roll, and it will be demonstrated later on out here in this angle here. And then I have one track for the signal for the tilt motor to rotate the propulsion motors. And then I have the just general speed controller signal to provide the signal to how much power the motors should have. And then there are 2 redundant ground tracks in the inner part here. So this is the setup right now. I can show you a picture here of how it looks in the copper laminate version. I think it's kind of difficult myself to understand what is rotating and what is static. So I just want to show you how it looks when I run this center pod here without the wings attached. They're going in here. But without the wings I can still demonstrate the yaw motor and how it keeps the craft in one direction. So let's turn it on, and let's also take this away. And since it's a traditional helicopter setup, I have to engage or disengage, I don't know which, the what is it called? It's the motor interlock. Well, so nothing happens if I start it now. I first have to arm it, of course. Wow, I have satellite lock, but still I don't have any motor action. But if I start this, I think I will have. Okay, so now we're simulating the wings turning. So here's the yaw input. So if I want to turn to the right, push right. I want to turn the craft to the left, push left. And if I start spinning the wings faster, it will still, let's keep it here. It will keep the position, and I can slow it down as well. And it will go back. Okay, I don't know how much clearer that was, but you can see the flight controller managed to keep the main tube and the flight controller itself and this yaw motor structure in whatever position I give it. And of course this is also where you would sit on sort of a structure up here, so that will also of course be in the direction you want. And the whole wing assembly with the batteries and everything, which actually is the majority of the weight, will move. So the motor doesn't have to do much job. I mean, this is all ball bearing like assembled, so it only just needs to decouple this mass from this mass and do it at a proper rate, but that's not much of a job. So this motor is it's not even getting cold. I mean, it's not almost doing any work at all. So the battery will last for a very long time in this setup. So the battery is mainly for the flight controller. Okay. Before we jump into the first two test sessions with the new Levitator, I just wanted to comment on the settings in the flight controller in the Arducopter. So I chosen to start out with the flight controller set up as a helicopter, a traditional helicopter H1 frame, and that means that the roll and the pitch and the collective servos are decoupled. They are not connected with a computer program which make them work like simultaneously doing this stuff. It's one servo for roll, one for pitch, and one for collective. And that's important because the Levitator needs to have those three axes separated. So this would be like a modern, traditional modern helicopter rotor head. So you have three servos spaced 120 degrees apart, and they together do the collective, and then the cyclic is like done in a computer program and sent out to do like both collective and also doing the cyclic thing all together. And it doesn't work in the Levitator. The Levitator needs to have all the control authority on the cyclic. You cannot use up control surface authority to act as a like up and down motion. You need to do that by spinning up the motors. So the throttle signal is coupled to the collective signal, but I don't have any collective servo in the Levitator, so that's just a ghost channel, and the motor, the ECS, like mirrors that setting, so they act as the collective, and the pitch and roll is only for the servos in the wing. So that's a good starting point, and then there are a bunch of other small setting changes you can do and have to do to make it do the right thing. I might do a separate video about that later on if I get everything to work appropriately. Okay, so let's take a look at the very first flight of this vehicle, and you have to bear in mind this was the very first time I assemble it outdoors, and you know, anything can happen. You might have forgotten some piece that just cancels the whole day, but I did manage to get it up in the air just barely. Let's have a look. Okay, so what happened there? Well, I started out with these motors. They're super cheap, but they're good for what they are. But the marking is wrong. And when you see a number on these motors, it's supposed to be the stator diameter times its width. So with the original motors from the Levitator, these are 5010 motors. So the stator, the electromagnet inside, is 50 millimeters diameter, and the depth of it is 10 millimeters. So a 5010 motor, so that's good. And these are marked as 4225 motors. So the stator is supposed to be 42 millimeter, and the depth is supposed to be 25, but they're not. They are 3508, so 35 millimeter diameter and 8 millimeter wide. So they are totally underpowered. They did manage to keep it in a low hover, but that was going full throttle, and they were really bogged down. So at that point they were turning the propellers at 63% of the no load RPM, and that means that you're pretty far down the efficiency curve, as opposed to these motors that can swing the propeller at like 81% of its no load RPM. So it's like in a perfect spot when it comes to the motor efficiency. But I did want to give it a second try. So the second flight I did pitch up the angle of attack of the main structure's blade, and that would potentially be enable me to squeeze out a little bit more power from these motors by like loading them down a little bit. And well, it did kind of work, so let's see. Okay, so that's not what you want to hear. So it turns out that I, during all the assembling and disassembling of this craft, managed to forget to put in a screw there. So it's positioning the bearing in the structure, and it popped out, so it started to wiggle around, and you could see that the craft did wiggle around a little bit. Okay, so it could hover a little bit higher, like 1.5 meters or so, but that's obviously not enough. I need to be able to fly this machine comfortably with one motor broken, and now it can barely stay in ground effect with 4 motors at full power. So yeah, obviously need to change the motors. So I'm going back to the 5010 motor, and the new machine weighs like 14 kilos and the old one 12 kilos. So I'm up around 20% in weight, but using the same motors in the original version, I will gain like 33% more power, and I have a corresponding battery pack upping the capacity 33% as well. So I expect to keep the performance or even slightly increase the performance and endurance. And I feel very comfortable flying with one of these motors off and 3 running in the new version. So in the upcoming videos, now I'm just waiting for better weather. It's early spring, so it's like coldish, sometimes warmish, and a lot of wind. But there are calm days, but they're far between. So I'm waiting for good weather, and then I will start exploring the tuning of the Arduplane program. And once I got a good feeling, that's good connection to the stick and the machine, I will explore the altitude hold functionality, and then progress to the GPS functionality with this loiter mode or GPS position hold. I don't really know what the difference is, but you know, parking the craft in the sky. And then after that, I will get into the interesting part of trying the potential redundancy features, and trying to fly 2 flight controllers at the same time and see how that works. So this flight season will be so interesting if I don't totally wreck the machine in the beginning. So I'm really looking forward to that. So I will see you in an upcoming video. Goodbye.